Hi guys, welcome back to another video. Before we begin, I do want to walk you through my Teams page. Every day, I've actually been posting announcements. So these announcements are very important and they give you a general sense of priorities for the day. And every announcement that I've been making, the first priority is completing those attendance surveys by 12 p.m. Okay, so you'll find these announcements every day in my page. I know that Miss Garcia is probably doing the same thing because she was the one that taught me how to make these announcements, but there's a lot of information here. Another item in my announcement for today, for Wednesday, is that if you want a school yearbook, then please scroll up to another announcement that I made yesterday night regarding how to acquire a yearbook. If you're willing to pay $50 for this yearbook, then head on to this announcement and complete the steps. Okay, so that's all the announcements that I have for today. I also want you to remain on my Teams page. I want you to go to the General Resources channel. We will be using a resource for today's lesson. So if you click General Resources and you go to Files, I uploaded a new resource called Bond Energy Table. So please have this resource handy for today. We will be using this table and we will be using it to determine bond energies of specific bonds. And I'll teach you how to interpret this table and why we will be using it. So please just have this open, have it aside, but do take out your journal and start writing today's title. I promise this is an easier lesson. It's actually the last lesson for Unit 8. Unit 8, I have to admit, was very difficult, especially because of all of the complicated math that I asked you to do, mixing equations with train tracks. It was a hot mess. But I want to finish this Unit 8 with something much easier. There's still a little bit of math, but it's simple, basic, for basic math, for basic function math. So it's not anything difficult. So just have this bond energy title in your journal, and then we will begin. And we will start with something that I want you to think about. So I have A and B. A, I have two hydrogen atoms and one oxygen atom that are not bonded to each other. And in B, I have H2O, and H is bonded to the oxygen. So which one do you think is more stable? Do you think water prefers to exist without any bonds, or does it prefer to have bonds? So just take a minute. So let's consider A, where I have my atoms that are not bonded to one another. In fact, hydrogen is separate from the other hydrogen and oxygen. And hydrogen, remember that it prefers to have two electrons. So it's actually seeking something for it to complete its two valence shell. Same thing with oxygen. Oxygen has 6 valence electrons and it's desperately looking for those 2 other electrons. So I would say that they're rather unstable. So if I actually combine and make bonds between the hydrogen and oxygen, notice that the oxygen will finally get its 8 electrons, and hydrogen will also get its 2 electrons that it was looking for. So they form a covalent bond. When I break bonds, I have to add energy to that molecule. And so the energy is very high for atoms that are not bonded to one another. And they release energy when I form bonds. So the H2O molecule with bonds is much stabler with lower energy. And that energy that was lost when I formed bonds was lost as heat. So write down the definition of bond energy. It is the energy released when forming a chemical bond. if you consider the law of conservation of energy, if I want to break that bond, it should be the same amount of energy. So it's also the energy required to break a chemical bond. So again, just a little summary of what bond energy is. It's the energy that's released when forming a chemical bond, or the energy that is required to break that chemical bond. If you remember back from one of our first lessons of Unit 8, was that I showed you what a chemical reaction diagram looks like, or the extent of this reaction coordinate diagram. In an exothermic reaction, the reactants are usually higher in energy than products. That means that the bond energies of my reactants are higher and the bond energy of my products are lower. And we can use these bond energies to calculate the change in heat of a reaction. And remember, you've also seen this definition. The enthalpy of a reaction, or the change in heat of a reaction, is the heat released or absorbed in the bonds in a chemical reaction. Determining the bond energy of bonds are very easy. It's super basic. So this question is asking, what is the energy of a carbon-fluorine bond? So the trick is that first you gotta determine whether this is a single, double, or triple bond. This CF, I only see a single bond. So I'm gonna just focus on single bonds only, which means I'm going to ignore this column because this column is double and triple bonds. The next step is to locate the CF. So I look at this column, no CF, look at the second column, and there you go. I found the CF bond, and its average bond energy is about 485 kilojoules per mole. That per mole means that I have 602 sextillion bonds, and all of the energy of those bonds equals to 485 kilojoules. Let's give you another example. So I have an OC bond, and it's a single bond, so I'm not going to focus on this third column. And I notice that there's no OC bond. So I have to flip this OC to CO because it's just a flipped molecule. So OC is the same thing as CO. So you look at the CO, which is in the second column, and the bond energy of CO, or OC, is 358 kilojoules per mole. Try to do this one on your own, noting that I have a double bond. So pause this video and determine what is the bond energy of the double bond nitrogen. I hope you said 418 kilojoules. Some of you might have confused this triple bond nitrogen, but please make sure that you notice how many bonds are in between these two nitrogens, because it is a huge energy difference. Okay, so good job. Pause this video and determine what the bond energy of NO is. So I hope you mentioned that it's 201 kilojoules. So good job. Pause this video again and determine the bond energy of O double bonded O. So I hope you said 495 kilojoules of energy. And I really do hope that you did not look at this single bond. Again, there's a huge energy difference between a single and a double bond. Even a triple bond is much more drastic. So this is the equation that we will be using to determine the change in energy of a reaction. And we're going to sum all of the bonds of the reactants and subtract all of the bond energies of the products. So I know this weird looking thing might look scary at first, but what this symbol represents, it's another Greek letter, and It's called sigma. Sigma just represents the summation of everything. So this sigma encloses the bond energies of my reactants minus the summation of all the bond energies of my products. So I'm going to determine every single bond energy of my reactants. I'm going to sum it all together, and that's the summation of the bonds broken reactants. Then I'm going to focus on the products. I'm going to sum all of those bond energies, and I'm going to subtract both the reactants minus the products, and I'll show you an example. But the first thing that I want you to do is, ignore that, write down these steps. So I need you to determine, or write down these steps to determine the enthalpy of a reaction. So pause this video, make sure you write down all 3 steps. So the first step is to draw every Lewis dot structure. And I think you should know how to do this. I've engraved this by repetition. And drawing Lewis dot structures is an important chemistry concept. Second step is to label all of the bonds with their bond energies. And the third step is to add the reactants and subtract the product bonds. And I'm going to show you how to do that exactly. So let's start out with something simple. So I have this reaction, and lucky for you, I have already determined the Lewis dot structures of my reactants and my products. So the first step is already done for you. And I'll be honest, for Unit 8, drawing out Lewis dot structures is not a concept that I'm testing you on, or the district is testing you on. So you will be getting the Lewis dot structures already given to you. So if you don't remember how to do it, don't panic. But I do recommend that you remember how to do them. Second step, I need you to label all of the bonds with energies. So I just want to focus on my reactants first. So in my reactant side, I have this CO bond, but this is a triple bond. What I'm going to do is I'm going to determine the bond energy of the CO triple bond. And so I'm going to look at this third column, and there are 2 CO bonds here. One of them is much more bigger than the other. But I need to remember that this is a triple bond, so I'm going to look at the 1072 kilojoules per mole. Notice that I only have one of them. My next step is to determine the bond energy of my HH bond. This is a single bond, and so I'm going to look at this energy value, which is 436 kilojoules. But I have 2 of these. And oh, I'm so dumb. I multiplied it times 3, which is not going to give you the correct answer. So I do apologize that this is, I started out wrong, but do the math and multiply 436 times 2. This is a simple error of mine. Let's focus on the products. So on my product side, I have a lot of bonds. So the first bond that I recognize is this CH bond. Why am I so popular today? So this CH bond, I have 3 of those. And I'm going to look at the CH bond in the table, and that's going to give me an energy of 413 kilojoules. I'm going to multiply that by 3 because I have 3 of those bonds. Another bond that I recognize is this CO bond. So this CO bond, I only have one of them, and I'm going to look up the energy on the table. So this is a single CO bond. It has an energy of 358. This OH bond, it's my last bond in this product, and that has an energy of 463 kilojoules. If I add all of those bond energies of my products, then I get 2060 kilojoules. My third step is to just subtract the total energy of my reactants minus the total energy of my product. But I made a mistake, so this number is not the correct answer. What I need you to do, and I know that you can do it because you are smart enough, determine the actual energy of the reactants, because I messed up on the number of hydrogen bonds that I had. So instead of 436 times 3, it's supposed to be times 2. And so this total reactant energy is also slightly different. So make sure that you catch my mistake. On the second example, I promise I am not messing up. Alright, so I have this reaction, and I have 2 moles of C2H2 plus 4 moles of H2, and that's going to give me 2 moles of C2H6. My first step is to determine the Lewis dot structures, and again, please don't panic. When I'm going to assess you on bond energies for this unit, I'm already giving you the Lewis dot structures. I don't want you to worry about getting the Lewis dot structures wrong. But this is what the Lewis dot structure of C2H2 looks like. But I have 2 of these. So I'm going to draw 2 C2H2s. And I also have H2 in my reactants, but I have 4 of them. So I'm going to draw 4 H2s. Go away. My products, it's a C2H6, and I have 2 of them, so I'm going to draw these 2 molecules out. So I have already finished drawing all of the Lewis dot structures. My second step, I'm going to label all of the bond energies, and the first bond that I recognize is the CH bond, and notice that I have 4 of them. So I'm going to multiply the bond energy of CH, which is 413 kilojoules, times 4. I also have a triple bonded C. So I have to look at this third column where I have all of my double and triple bonds. This is a C triple bond C, and it has a value of 839 kilojoules. But because I have 2 moles of C2H2, that means I'm going to have 2 bonds of C, triple bond C. And so that's why I multiplied the 839 value times 2. I also have 4 bonds of HH bonds, and that has a value of 436 kilojoules. I'm going to multiply it by 4. I'm going to add all of that up, and that should give me approximately 5,074 kilojoules. So the summation of the bond energies of my reactants is 5,074 kilojoules. So this is just the reactants. I need to do the same thing for my products. So I'm going to focus on each bond for my products, and the bond that I see first is the CH single bond, and that is 413 kilojoules. Each molecule has 6 CH bonds, but because I have 2 molecules in my reaction, it's times 12. Another bond that I have is that CC bond, but this CC bond is single. So I'm going to use this CC bond that has a value of 348 kilojoules. If I add all of the CH bond energies and the CC bond energy, then that gives me a total of 5,304 kilojoules. My third step is to just subtract the reactants and the products. So I'm going to subtract 5,074 minus 5,304. Notice that this is going to give me a negative energy value, and that's okay. Remember that an energy change in heat represents an exothermic reaction. So because this reaction is negative 230 kilojoules per mole, then that means that this is an exothermic reaction. So I hope this wasn't too hard. It shouldn't be too hard. All you're doing is adding all of the bond energies of the reactants, then you're adding all of the bond energies of the products, and then you're subtracting both of them. The tricky part is making sure that you recognize all of your bonds and determining which bond, either single, triple, or double, the molecule has. So please make sure you pay very close attention to the number of bonds and to the type of bond. That is actually it. I'm going to post an assignment that's super basic, and please tune in for Monday's lesson. We will be starting a new unit. So thank you and have a great day.